So we're going to work through the basics of limits of trig functions, and then we're going to do an example after we explore just a little bit about how sine, cosine, and tangent are used when finding limits. So just as a polynomial is continuous, meaning that when you're graphing a polynomial, such as 3x squared plus 4, so when you're graphing it, it's going to be continuous. That means that we do not have a domain restriction, such as a asymptote or a hole in the graph. So it'll just be a continuous graph, and you'll never lift the pen off the paper. That's literally what that means, continuous. So because we do have similar properties in sine and cosine, you can look at this chart that I've inserted here for cosine, which is blue, and sine x, which is yellow, and see that it is continuous. It's infinite. So you're never picking your pen up when you're graphing this and then continuing on in a different place. Because it has those similar properties, we can do the same thing in that as x is approaching any value a, we can substitute a and say that the limit of x approaching a for sine of x is equal to sine of a. And the same thing for cosine. The difference with tangent, as you can see, I have another chart here that shows where tangent has its asymptotes, which is at pi over 2, at 3 pi over 2, and continues on from there. So we can say that tangent is essentially sine x over cosine x, but we would have to say that for cosine of x, it cannot equal 0, and it equals 0, or we would say that the tangent will equal 0 essentially for a basic trig function. It would be at pi over 2 and 3 pi over 2, and that's where the asymptote would occur. So as long as we keep that in mind, then what we can do is we can say that the limit of tan x is equal to sine x over cosine x, and use our limit property, which allows us to split apart our division, and we would say that this is going to be equal to the limit, and we'll just place limit inside then of x as it approaches a for sine of x divided by the limit as x approaches a for cosine of x. And because we've just established that for each of these, for sine and cosine x, that we can replace them with a, we can then further say that this is equal to the sine of a divided by cosine of a. And when we do that, it allows us to solve this down into a basic notation such that the limit of as x approaches a for the tangent of x get rid of this, make this a little cleaner, sorry about that. So we can say that, rewrite this as the limit of x approaching a for tangent of x is therefore tan of a with the restriction of x not being equal to 0 at pi over 2, 3 pi over 2, and so on and so forth for each pi k. So as you can see, it's from pi over 2 to 3 pi over 2. That's pi radian. So if we just say that it's plus pi k, then we can determine any infinite 0 or asymptote that it might have as a restriction from there on out. So let's take a look at an example. And in this example, we're going to first start with a basic limit of as x approaches, and let's eliminate that a. That's actually supposed to be 1. So let's do that real quick. And we're going to learn that there is one more property, which essentially in this case is going to be the opposite of composition. But composition, if you remember, F composed of G, which would look like F as it is composed of G of X. That's a composition. We're going to work that in reverse a little bit to show how this works and why we are allowed to do it. But essentially, first we can say that this is going to be equal to the cosine of the limit as x approaches 1 for x squared minus 1 over x minus 1. And that allows us to simply look at just this inset, and then we can determine what the limit might be from there using our various steps. So the first step says to go ahead and place 1 inside here and see what we end up with. So we'd have 1 minus 1 over 1 minus 1, which is going to give us division of 0 divided by 0, which means that there is a hole in the graph, but there is also a way to factor and reduce this to a form that might allow us then to move forward and determine our limit. So in this case, we've worked with this before several times. We're going to say that this is equal to the cosine of the limit as x approaches 1. And in the numerator, it's the difference of squares, which means that we have x minus 1 times x plus 1 divided by x minus 1. And now we can see how we can factor out the problem in the denominator. So we're going to end up reducing these equal terms, leaving us with just the cosine. And actually, we'll rewrite this now. We can recompose this so that we have the limit as x approaches 1 for cosine of simply x plus 1. And now we can find out, well, what is that limit? And the limit for this is actually going to be 1 plus 1. We're just going to, since this is now a polynomial, we're simply going to place the value that x is approaching from the left and the right into, or insert it in, for x. So that's going to give us the cosine of 1 plus 1, which is 2. And that is our first example. I'm sure I'll do a few more. But thanks for watching. Hope that helps.